everyone. So, PROMPT stands for Preparedness for Operational Monitoring and Prediction of Contaminant Transport in the Sea. Now, the sea spans a vast area. To efficiently predict the contaminant transport, we need to focus on a portion of it. Which one? Well, Professor Besio already gave you the answer. Anyway, let me recall it. Starting by telling you the story of the crude carrier Haven, which in 1991, while anchored off the coast of Genoa, suffered a catastrophic explosion that spilled more than 10,000 tons of oil into the sea. This event caused a severe contamination along the Ligurian coast, but also along the French one. And it remains the largest spill ever recorded in the Mediterranean. Yet, the Haven is just one of many. In the past 4 years only, about 2 million hectares of oil have been detected on the Mediterranean surface using Sentinel-1 satellite images. The main sources of spill are accident, so ship collisions or grounding on shallow water, illegal dumping, when ships intentionally release oily waste into the water, and operational spills due to routine operation as loading or unloading cargo or a leak from storage tanks. If the first two causes, accident and illegal dumping, can happen anywhere, often in the open sea, where our prevention efforts are limited on monitoring and detection, operational spills mainly occur inside the ports. According to the EMSA, ports are the area where most of marine accidents occur. This happens because ports are high traffic zones where vessels maneuver in restricted area, really increasing the likelihood of accident, grounding, and spill. But this also offers an opportunity. The relatively confined nature of ports make them ideal for hydrodynamic modeling. By leveraging advanced hydrodynamic simulation, we can predict pollutant path, we can identify vulnerable areas, finally, we can plan effective mitigation strategies, one of the key goals of PROMPT. So the arrival point of my presentation will be this one, understanding how to track pollutants, specifically oil and hazardous and noxious substances, into the sea. To do so, we need, first of all, to understand how the currents drive the water movement in the domain. This, in turn, requires selecting and analyzing all the environmental variables involved in the generation of currents. By following this step-by-step approach, we will gain a clear understanding of pollutant transport. Then the dispersion insights will be combined with a risk analysis to have a comprehensive understanding of the most vulnerable areas along the Ligurian coast. And finally, the results will be made accessible through a web platform. Let's explore now each of the orange sections, starting from the first one, the selection of relevant metocean scenarios. Local current are generated by a combination of tide, large-scale current, wind, and wave. When predicting metocean events, the common approach is to look at historical data by assuming that future events will resemble those of the past. For this analysis, we focus on wind and wave and start looking at a hindcast we have in our department, which covers the last 40 years of hourly wind and wave data. For example, in the Ligurian Sea, we have a data set in correspondence of each point on the map. So we select the point of interest, highlighted by the red ring, and through a clustering algorithm, we investigate these 40 years week by week, and we group the weeks in function of wave similarities, such that if 2 weeks have similar wave height and wave period, they pertain to the same group because they are describing the same event. Here you see, as example, 2 groups with the relative significant wave height. One group is highly populated, the other one is poorly populated because it refers to rare extreme events. Then from each group we select the most representative week, the red lines in the examples, and that's it. We have a small and manageable set of scenarios able to capture all the environmental dynamics in the domain. So we have wave and wind from our hindcast. We simply download the tide and regional currents from some reliable providers. Now, with all the environmental variables gathered, we can move on implementing the hydrodynamic modeling, which basically means combining the environmental variables with the bathymetry, the geographical information of the domain down in the slide. The forcings are imported as shown on the top plot. So wave, tide, large-scale currents along the external boundary, the blue horizontal line, to allow the model propagate them toward the coast. Wind is applied at specific location, the orange stars, then the model interpolated to have it uniformly distributed. The model runs for each scenario and gives us the velocity field. Here you see the surface velocity field average over one of the selected weeks. The most crucial part when dealing with modeling is the validation. To trust the results, we need to compare them with real-world data. In this case, we compared the water level model with the water level measured inside the port in correspondence of the red dot. The box plots summarize the results. The first two boxes show the errors, so the discrepancies between model and observation. They're very low, revealing a good agreement. The other two boxes show the correlation between model and observation, and they tend to 1. So in general, we can say the model is able to properly capture the real-world dynamics, and we can rely on this result for further analysis. Finally, we can simulate the dispersion of pollutants, oil and hazardous and noxious substances. This is done with a separate model that solves the advection diffusion equation, which simply tells us how the currents drive the pollutants, combined with a weathering model to take into account the interaction between the pollutant and the surrounding environment. In fact, once both oil and HNS are released into water, they undergo several physicochemical processes, which depend on the type of pollutant, the spill characteristic, and the environmental condition. The images show you all the mechanisms involved. They're also listed in the green table. And as you can see, there are so many processes going on here that really make the problem challenging to address. But as we know, we work with the weekly scenarios because we simply focus on early intervention, as the most critical actions must be taken in the very first few days after a spill. And some of these processes have a response timescale greater than a week, so we will only focus on the following key ones highlighted in bold. Spreading, which is the horizontal expansion of the slick due to mechanical forces, as gravity or inertia. Dissolution of the, in general, small soluble compound. Evaporation of the volatile component. This decreases the toxicity of the spilling water, but of course increases the one in the atmosphere. That's why in Prompter we include also an atmospheric model. Then evaporation in general takes place very, very quickly, so it turns to be the most important process, together with the last one, beaching, when particles get stuck. Here on the left, you see the releasing positions we selected for our simulation, for oil on the top, chemicals down. Oil has been released along the main vessel route. Red dot indicate a spill from a large cargo, cargo ship or cruise liners. Down, while the black dot, a spill from a smaller pleasure boat, which usually use a lighter fuel. Down, the chemicals have been released in correspondence of two deposits, one in Multedo, one in Porto Antico. There are two graphs on the right showcasing the weathering model results. On the top, for automotive gasoline, which is a light fuel, you can clearly understand how important it is to properly model evaporation, represented by the green line. In fact, after the first 2 hours, about 60% of the oil is evaporated. Down, for palm oil, which is neither volatile nor soluble, beaching, the orange line, is definitely the most predominant process. To support the mitigation strategies, we developed two key analyses. Again, the results are reported for the oil on top, chemicals down. On the left, we look at the estimation time of arrival, which addresses the question, how long will it take for a spill to reach a specific location? The minimum time across all the scenarios is evaluated and used for the plot. On the right, the hazard map, where hazard is defined as the probability that the spill reaches a specific location. This probability is summed across all the scenarios and used for the plot. So they give a general and explanatory, but not exhaustive understanding of the risk associated with spills inside the port. Okay, so we have seen how step by step the fate of a spill can be predicted through simulation. The results reveal that most of the leak substances either evaporated or deposited along the docks or breakwater structures, And this highlights two important aspects. The concentration of the pollutant within the port boundaries could lead to a water quality degradation, potentially affecting the local ecosystem. But on the other hand, the concentration of the pollutant within a restricted area decreases the risk of widespread contamination, really simplifying recovery efforts. The next step will be to combine these results with a risk analysis to have a comprehensive understanding of the most vulnerable areas, both along the Ligurian coast and within the port. And then to further support stakeholders and decision makers, we will implement a web platform. I'm not going into details because the next speaker will do it. I just want to say that I saw the preview yesterday and it's super cool. But more than cool, it's super useful. I'm sure it will definitely empower users to plan and respond more effectively, mitigating the impact on marine ecosystem, and maybe preventing the spill to reach the coast as occurred here in Genoa in the 1991 accident. And thank you.